Hello, in this video we're going to look at a classic example of how to impose boundary conditions for a potential flow, the Milne-Thompson circle theorem. So to look at how to apply the Milne-Thompson circle theorem, let's just start off by considering a potential flow of complex potential, and I'm going to call this complex potential f of z. That's going to allow me to use W as my result in the end. So to create, the idea is to create a boundary on the circle. So you have in mind looking at the flow past the cylinder, and then further down the line looking at, for instance, the deformation of the cylinder to give us ellipses, to give us airfoils, and so on and so forth. And that theorem allows us to do this very simply. So to create a circular boundary on the circle, and the circle is defined as the modulus of z equals a, then all I need to do is to write down my complex potential W of z as f of z. Okay, so that's the flow that I want to look at, and to this I'm going to add f of a squared over z bar. And I am taking the over bar of this, where the bar denotes the complex conjugation. Okay, so well, let's just check that. So, well, the circle is defined as z equals a times the exponential of I theta for theta in and this is 0 to pi. Okay, so that is the definition of our circle in complex notation. And this is a circle of radius a, and a radius. Okay, and well, let's just have a look at what this this complex potential is equal to on the circle. So W of a times exponential of I theta equals f of a times the exponential of I theta. And then to this, I'm going to add this quantity, and therefore I'm adding f of a squared divided by a times e to the I theta. I'm taking the bar of this thing, and I'm taking the over bar of everything. So let's just have a look at this. So if I am writing this to simplify this complex notation that I'm getting here, f of a squared over, well, a is a radius, it's a real number, so I'm going to keep this, this is a real number, so that's a, and e to the I theta complex conjugated becomes e to the minus I theta. Okay, close the parentheses, and I take the overbar of that thing. So what I get is f of a e to the I theta, a squared over a, well, that's a, and 1 over e to the minus I theta is e to the I theta. So I get plus f of a e to the I theta, and the whole thing is overbarred. Ultimately, what I get is a complex number to which I add the same complex number conjugated. Okay? And so the result is a real number. So what we get out of this is that what we've demonstrated here is that by applying this formula, what we've created is that for any potential, any complex potential f of z, we've imposed that z equals a times e to the I theta is a streamline. And therefore we've just verified this theorem. So for instance, we can just take an example. And the example that I'm going to take is that of a uniform flow. So imagine that you have f of z equals u0 z e to the minus I alpha. So this is a uniform flow of velocity u0 and incidence alpha. Okay, so if I write this down, then I can just write down W of Z. And, well, remember how we do this. We write down, first of all, f of z, so that's u0 z e to the minus I alpha. And then I'm going to add this f of a squared over z bar, the whole thing overbarred. So then I get plus u0 e to the minus I alpha. Okay, and instead of z, I'm replacing by a squared over z bar. And I need to take the overbar that thing. So let's simplify this notation. So that's u0 z e to the minus I alpha plus, well, my velocity is a real velocity. I've taken, well, this is kind of typical in these complex potential notation, that the direction of the velocity is carried by, and therefore the imaginary component is carried by the exponential. So u0 remains u0. Then this e to the minus I alpha becomes e to the I alpha. I'm taking the complex conjugated of it. A is a real number, it's the radius, so it stays a, so a squared. And z, 1 over z bar over bar is just 1 over z. Okay? So that can be simplified by just factoring everything by u0. And then we get u0 z e to the minus I alpha plus plus a squared over z e to the I alpha. And that is essentially what the flow would look like, a flow with a circle as a boundary. And it's just a horizontal flow with incidence alpha. So maybe I'm going to make it with a slight incidence like this. This is what this flow is going to be written. This is how this flow is going to be written in complex potential notation. Okay? This concludes this video on the Milne-Thompson circle theorem.